What if I told you that every sip of your morning coffee is not just a daily ritual, but a perfectly engineered chemical experiment happening inside your body? You see, what looks like a simple cup of brown liquid is actually the result of a billion microscopic reactions. Reactions that manipulate heat, molecules, and your brain's very chemistry. When boiling water touches the roasted beans, it triggers what scientists call the Maillard reaction, a complex dance between amino acids and sugars that produces hundreds of new compounds. These compounds give coffee its color, its signature aroma, and that slightly bitter yet satisfying taste that millions of people can't live without. In fact, over 800 volatile aromatic compounds are released as the hot water extracts the oils and caffeine. This vapor that rises from your mug, it's not just smell. Those molecules literally enter your nose and stimulate the olfactory receptors connected to your limbic system, the emotional core of your brain. That's why the smell of coffee can instantly make you feel happier, calmer, and more awake before you even take a sip. Now let's get inside your body. As soon as caffeine hits your bloodstream, it locks horns with a molecule called adenosine, a neurotransmitter responsible for making you feel tired. Think of adenosine as your brain's natural slow down signal. Throughout the day, adenosine builds up, making you drowsy. But caffeine, it's a master of disguise. It fits perfectly into adenosine's receptors, blocking them, and in doing so, it tricks your brain into thinking you're not tired. Your neurons start firing rapidly, your adrenal glands release adrenaline, and your heart beats a little faster. You suddenly feel sharper, more alert, more alive. But here's the twist. Caffeine doesn't actually create energy. It just hides your fatigue by manipulating your brain chemistry. And when its effects fade, adenosine floods back in, causing that familiar afternoon crash. Still, scientists have discovered something remarkable. Moderate caffeine intake actually helps protect your brain from neurodegenerative diseases like Alzheimer's and Parkinson's. Studies suggest that caffeine's antioxidant properties reduce brain inflammation and help neurons communicate more efficiently. But the magic doesn't stop there. Coffee's dark color comes from melanoidins, antioxidant compounds that slow down aging and boost metabolism. And the little burst of dopamine you feel after your first sip? That's the same pleasure signal triggered by music, love, or even achieving a goal. So every morning, without realizing it, you're conducting your own chemical experiment, one that blends physics, biology, and chemistry in a steaming cup of comfort. The next time you sip that freshly brewed coffee, remember, it's not just waking you up, it's fine-tuning your brain, rewiring your mood, and fueling the scientific marvel called you. Mind blown yet? You flip a switch and boom, your room floods with light. But have you ever stopped to think, what really happens in that split second? How does invisible electricity suddenly turn into brilliant light that cuts through darkness? This ordinary act, turning on a light, is one of the most mind-blowing pieces of applied science in human history. Let's break it down. Inside that little glass bulb lies a tiny metal filament, often made of tungsten, a metal with one of the highest melting points known to man, over 3,400 degrees Celsius. When you flip the switch, an electric current flows through this filament. Now here's the wild part. Electrons start racing through that wire at near light speed, colliding with tungsten atoms and transferring energy to them. As these atoms vibrate violently, they heat up, but instead of melting, the tungsten glows. That glow? That's incandescence. Matter emitting light because it's so hot. The filament shines at roughly 2,500 degrees Celsius, turning pure electrical energy into visible light. But that's not all. What keeps the filament from instantly burning up is the presence of an inert gas, usually argon or nitrogen, inside the bulb. These gases prevent oxidation and allow the filament to last longer. Without them, it would burn out in seconds. Think about this. Your light bulb is basically a controlled fire trapped inside glass, a mini sun sitting on your ceiling. The science of glow. Here's something that will really blow your mind. Only about 10% of the energy in a traditional bulb becomes light. The other 90% is lost as heat. That's why incandescent bulbs feel warm to touch. Modern science improved on this with LEDs, or light-emitting diodes, which produce light through electroluminescence, not heat. In an LED, electrons don't make atoms vibrate. Instead, they jump between energy levels inside a semiconductor material. When they fall from a higher energy state to a lower one, they release photons, packets of light, directly. That means LEDs create light without needing high temperatures. They're cooler, faster, and up to 90% more energy efficient. What's even more fascinating, the color of LED light, warm yellow, pure white, even neon blue, depends on how much energy those electrons release during their jump. Change the semiconductor material, and you change the color of light. You can literally design light with math and physics. The deeper impact. The light bulb didn't just brighten rooms, it brightened humanity's path. When Thomas Edison perfected his design in 1879, it extended the human day beyond sunset. Productivity, safety, and technology exploded. Cities became alive after dark. Factories worked 24 hours a day. Art, science, and communication flourished, all because humans could finally control light. Today we take this miracle for granted, yet behind every glowing bulb lies the legacy of countless experiments, failures, and moments of genius. So the next time you turn on your light, remember that tiny click of a switch is a symphony of electrons, atoms, and human ingenuity. Light isn't just illumination, it's proof that we've learned to command nature's most powerful force, energy, and bend it to our will. Mini mind twist. If you could see all wavelengths of light, not just the visible spectrum, every bulb would glow like a star, radiating invisible infrared and ultraviolet waves around you right now. That's the unseen beauty of physics working quietly inside your home. Every morning, millions of people hear that familiar whistle, the sound of water boiling in a kettle. But have you ever wondered what's really happening inside that bubbling chaos? That simple, everyday act, boiling water, is actually one of nature's most powerful transformations, powered by invisible physics and energy transfer at the molecular level. When you place a kettle on the stove, heat from the flame or electric coil begins to flow into the water. At first, nothing seems to happen, but at the microscopic level, something incredible begins. Water molecules start to absorb that thermal energy and begin to vibrate faster and faster. Each water molecule is like a tiny magnet, one side positive, hydrogen, and the other negative, oxygen. These molecules constantly attract and stick to each other with what scientists call hydrogen bonds. But as the temperature rises, the vibrations become so intense that those bonds start breaking apart. The molecules gain enough kinetic energy to escape from the liquid and turn into vapor, steam. This is the boiling point, 100 degrees Celsius or 212 degrees Fahrenheit at sea level, when the vapor pressure of water equals the surrounding air pressure, allowing bubbles of gas to form freely. Now, here's the part that blows minds. During boiling, the temperature of the water stays constant, even though it's still being heated. Where does that extra energy go? It's used as latent heat of vaporization, the hidden energy that converts liquid into gas without changing temperature. Each gram of water needs about 540 calories of energy to turn into steam. That's massive. This means even though the thermometer shows 100 degrees Celsius, the molecules are absorbing tons of hidden energy to break free from the liquid state. It's the same principle behind clouds, rainfall, and even hurricanes, all powered by this invisible phase change energy. Ever wondered why your kettle whistles? That's physics playing music. As steam rushes through a small opening in the kettle spout, it vibrates the air, just like how a flute works. The pitch rises as the pressure increases until the boiling point is reached. That high-pitched sound is literally steam molecules dancing with air waves. This tiny act of boiling combines thermodynamics, acoustics, and fluid dynamics in perfect harmony, all inside your kitchen. Boiling water might look simple, but it's a cornerstone of civilization. From cooking food safely, generating electricity in power plants, to sterilizing medical equipment, this single process defines progress. In fact, every thermal power plant, coal, nuclear, or solar, uses the same idea. Boil water, create steam, and spin turbines to generate electricity. Yes, that morning kettle whistle is the same science that powers entire cities. If you could instantly boil all the oceans of Earth into steam, the expansion would be enough to destroy the planet's crust from pressure alone. That's the scale of energy hidden inside simple water. Calm, clear, and unimaginably powerful. When you see bubbles rising, they aren't air. They're pure water vapor. Each bubble is a small, temporary universe of molecules fighting gravity to escape into the sky. The moment it pops at the surface, that vapor vanishes into the air, joining the endless cycle of the water we breathe, drink, and live from. It's poetic science, transformation, movement, and balance. You see it every day. Ice melting in a drink, a glacier dripping in the sun, or frost vanishing from your car window. But have you ever realized that every melting ice cube is a battlefield of physics and chemistry? What you're actually watching is a molecular-level war between structure and energy. At first glance, ice seems simple, just frozen water, right? But zoom in and it becomes a masterpiece of geometry and balance. Each water molecule is locked in a crystal lattice, bonded with its neighbors by hydrogen bonds. This creates a hexagonal arrangement, the reason snowflakes have 6 sides. Now here's something mind-blowing. This molecular structure is less dense than liquid water. That's why ice floats. It's one of the very few solids in the universe that is lighter than its liquid form. This property is the reason life exists on Earth, because lakes freeze from the top down, not bottom up. Otherwise, all aquatic life would freeze to death every winter. The moment ice encounters heat, molecules near the surface start absorbing energy. These vibrations break the rigid hydrogen bonds holding the molecules in place. They begin to move more freely, slipping and sliding, transforming from solid to liquid. But like boiling, the temperature doesn't rise immediately. All the incoming energy goes into changing the state, not the temperature. This is called the latent heat of fusion. To melt 1 gram of ice, it takes 80 calories of heat energy. Imagine that's the same amount of energy needed to raise 1 gram of water by 80 degrees Celsius. So melting is no small event. It's a huge energy transaction at the molecular level. Here's where things get even more fascinating. As the ice melts, it doesn't all disappear at once. The outer layers turn into water while the inner core remains solid, a perfect metaphor for nature's balance between chaos and stability. Scientists call this phase equilibrium, a state where melting and freezing happen simultaneously. Even as ice melts, some molecules refreeze at the same rate. It's a delicate dance, happening billions of times per second. This invisible equilibrium explains how glaciers can exist for thousands of years, constantly melting and refreezing in harmony with their environment. Now, scale this process up, from your glass to the planet. When global temperatures rise, polar ice caps begin to melt faster than they can refreeze. This upsets the Earth's natural balance. Melting ice contributes to rising sea levels, climate instability, and even changes in ocean currents.
These aren't just environmental issues. They're global chain reactions of thermodynamics. A single iceberg melting seems harmless, but collectively, billions of tons of ice are altering the energy balance of our entire planet. If all Antarctic ice melted, the global sea level would rise by over 58 meters, 190 feet. The melting of glaciers releases trapped ancient air bubbles, some over 800,000 years old, providing scientists with snapshots of Earth's past atmosphere. Ice reflects sunlight, while liquid water absorbs it. This albedo effect accelerates global warming once ice disappears. Nature's balance again, hanging on a thread of molecular physics. Here's a scientific paradox for you. When ice melts, the temperature stays the same, but entropy, or disorder, increases. In other words, melting is not just physical. It's a story of chaos taking over order. And the universe, as we know it, always moves toward disorder. That's why time moves forward. That's why nothing lasts forever. Not even ice. Every time you watch an ice cube melt in your drink, you're witnessing the same force that shapes planets, drives weather, and governs stars. Melting is not destruction. It's transformation. It's the law of change, from solid to liquid, from stillness to motion, from simplicity to complexity. So next time, before that last cube disappears, remember, you're holding the universe's oldest story in your hand. Nothing stays frozen forever.
Imagine this. You're reheating last night's pizza, and within seconds, it's hot and ready. Simple, right? But what if I told you this everyday kitchen appliance was born out of accident and wartime radar experiments? The story begins in 1945, when engineer Percy Spencer was testing a magnetotron, a device used in radar technology. During his work, he noticed something strange. The chocolate bar in his pocket had melted. Curious, he placed popcorn kernels near the radar tube, and boom, they popped instantly. This accidental discovery led to one of the most important kitchen inventions in human history, the microwave oven. But how does it work? Microwaves are a form of electromagnetic radiation, similar to light waves, but longer in wavelength. The oven directs these waves into the food, causing water molecules inside to vibrate rapidly, generating heat from within. Unlike traditional stoves that cook from the outside in, microwaves cook from the inside out, making the process lightning fast. Here's the science twist. The specific frequency, 2.45 gigahertz, is chosen because it efficiently excites water molecules while being safe for use in homes. That's why your plate might stay cool, but your food comes out steaming hot. Interestingly, early microwave ovens were huge machines, some weighing over 300 kilograms. It wasn't until the late 1960s that they became compact and affordable enough for regular households. Today, over 90% of American homes have one. Beyond convenience, microwave technology plays a key role in modern medicine, communication, and astronomy. From heating lab samples to helping scientists map cosmic background radiation. So, next time you hit that start button, remember, your kitchen microwave carries the legacy of radar science, electromagnetic energy, and one man's melted chocolate bar.
When was the last time you blew soap bubbles? They look like a child's toy, but in reality, they're a perfect example of physics, chemistry, and light behavior working together. A soap bubble forms when a thin film of water is trapped between two layers of soap molecules. These soap molecules act like tiny shields, reducing the surface tension of water and allowing it to stretch into a delicate sphere. But why always a sphere? Because a sphere is the most efficient shape. It holds the most air for the least surface area, minimizing energy. Now let's talk about the colors. When light hits the bubble, some of it reflects off the outer surface, and some penetrates and reflects off the inner layer. These two light waves interfere, sometimes canceling each other out, sometimes amplifying, creating the mesmerizing rainbow colors you see. This phenomenon is known as thin film interference, the same effect seen in oil slicks or butterfly wings. But there's more science hidden here. Bubbles can even be used in mathematical modeling to study minimal surfaces and energy distribution. In physics, they demonstrate how forces balance perfectly: gravity pulling down, surface tension pulling in, and air pressure pushing out. In fact, scientists at MIT and NASA study bubbles to better understand fluid dynamics in microgravity. In zero gravity, bubbles behave very differently, perfectly spherical and floating aimlessly. Fun fact, in 2019, researchers created a bubble that lasted 465 days using a special glycerol water mixture that slowed evaporation and stabilized its structure, proving that even the simplest childhood wonder can unlock complex physics mysteries. So, the next time you see a soap bubble floating in the air, know this: you're witnessing one of nature's most delicate and mathematically perfect masterpieces.
When you look in the mirror, you see yourself. But have you ever wondered how this everyday object performs such a perfect illusion? It seems ordinary, yet the science behind a mirror is pure magic wrapped in physics. A mirror works through the principle of specular reflection, when light rays bounce off a smooth surface at exactly the same angle they arrive. Unlike rough surfaces that scatter light in all directions, mirrors reflect light uniformly, creating clear and crisp images. The typical household mirror is made of a thin layer of aluminum or silver coated on the back of a glass sheet. The glass itself isn't what reflects the light, it's the metal coating that does the job. The glass merely protects the reflective layer from damage and oxidation. Now, let's explore a deeper level, the optical physics. When light from your face hits the mirror, each ray bounces back at the same angle, following the law of reflection. Angle of incidence equals angle of reflection. This creates a virtual image that appears to be behind the mirror, even though it's just an illusion created by light paths. Here's something mind-blowing. Mirrors don't actually flip left and right. They flip front to back. Our brain interprets this as a side-to-side reversal because we're used to imagining ourselves turning around to face the same direction as our reflection. But the story doesn't end there. Modern science uses mirrors far beyond your bathroom. They're vital in telescopes, lasers, solar concentrators, and even quantum computing. For instance, the James Webb Space Telescope has a 6.5-meter-wide golden mirror made from 18 hexagonal segments. Each segment reflects infrared light from distant galaxies billions of years old, helping scientists peek into the early universe. So, next time you stand before a mirror, remember that simple reflection holds the same laws of physics that allow humanity to explore the stars.
Every morning, billions of people around the world begin their day with a cup of coffee. But behind that comforting aroma lies a fascinating world of biochemistry and brain science. It all starts with the coffee bean, actually the roasted seed of a fruit called the coffee cherry. During roasting, heat triggers the Maillard reaction, the same chemical process that browns bread or sears steak. This reaction produces hundreds of complex compounds, the source of coffee's rich flavor and aroma. The real science, though, begins when you take that first sip. The key active compound, caffeine, is a natural stimulant. It works by blocking the action of adenosine, a neurotransmitter in the brain responsible for making you feel tired. Normally, as the day goes on, adenosine levels build up, signaling your brain that it's time to rest. Caffeine sneaks in, mimicking adenosine's shape, and binds to its receptors, but without triggering the tiredness signal. As a result, your brain stays alert and releases more dopamine and adrenaline, boosting focus, mood, and energy. That's why coffee feels like magic fuel for your brain. But coffee's chemistry doesn't end there.
It also contains antioxidants such as chlorogenic acid, which may help reduce inflammation and protect cells from damage. Studies suggest moderate coffee consumption can lower the risk of Parkinson's disease, type 2 diabetes, and liver problems, though too much caffeine can lead to anxiety or insomnia. The fascinating part? Each brewing method, espresso, French press, cold brew, changes the chemistry slightly. Temperature, pressure, and grind size determine how much caffeine and flavor compounds extract from the beans. It's both an art and a science. So next time you take that aromatic sip, remember, you're not just drinking coffee. You're engaging in a finely tuned chemical experiment that energizes your mind through molecular precision. When you blow a soap bubble, it seems like a moment of childlike fun, a sphere of rainbow colors floating through the air. But behind that delicate beauty lies astonishingly complex science. A soap bubble is more than air and water. It's a thin liquid film made up of 2 layers of soap molecules with a thin layer of water trapped in between. This structure forms because soap molecules have 2 ends, one that loves water, hydrophobic, and one that hates it, hydrophobic. When you make soap with water and blow air into it, these molecules arrange themselves so that the water-loving ends face inward, protecting the water, while the outer ends face the air. This delicate balance creates surface tension, a force that minimizes the surface area of the bubble, shaping it into a perfect sphere. In fact, a sphere is nature's most efficient shape, using the least energy to enclose a given volume. But what about the mesmerizing rainbow colors that dance across a bubble's surface? Those aren't dyes. They're the result of light interference. When light hits the thin film of the bubble, some light reflects off the outer surface and some off the inner. These waves overlap, amplifying some colors and canceling others, creating a shifting spectrum that depends on the film's thickness. Even more fascinating, bubbles play a big role in science and engineering. They're used in fluid mechanics, aerodynamics, and even medical imaging to study how gases behave in liquids. NASA scientists have studied bubbles in zero gravity to understand how fluids behave in space. And yes, the next time you see a child chasing a soap bubble, remember that it's not just air wrapped in color, it's a living experiment in physics, chemistry, and light.
If someone told you 100 years ago that you'd carry the power of millions of computers in your pocket, you'd probably laugh. Yet, here we are. Smartphones have transformed from simple calling devices into compact supercomputers that combine physics, chemistry, engineering, and artificial intelligence in one sleek gadget. At its core, a smartphone operates through billions of transistors etched into tiny chips made from silicon, one of Earth's most abundant elements. Each transistor acts like a microscopic switch, controlling electrical current. When combined, these switches process millions of calculations every second, powering everything from your camera to your favorite app. But there's more. The touchscreen itself is a wonder of science. It works using capacitive sensing, which detects the tiny electrical charge of your fingertip. The glass is coated with transparent conductors like indium tin oxide, allowing it to register even the slightest touch instantly. Then there's the camera, a masterpiece of optics and quantum physics. Modern phone cameras rely on CMOS sensors that convert light particles, photons, into electrical signals. This process is so precise that a tiny lens can capture details at the molecular level. Even your battery is a product of intense electrochemical engineering. The lithium-ion cells inside store energy by moving lithium ions back and forth between electrodes. This same technology now powers electric cars, drones, and even spacecraft. Finally, what ties it all together is AI and software engineering, enabling your phone to recognize faces, translate speech, and even predict what you'll type next. Your smartphone isn't just a piece of technology. It's a living example of how centuries of scientific discovery can fit in the palm of your hand.
Science isn't just locked away in labs or written in textbooks. It lives around us, in every ordinary moment. From the cup of coffee that wakes us up to the smartphone that connects us across the world, Every simple thing hides layers of brilliant physics, chemistry, and engineering. When we take a closer look, we realize that our world is built upon miracles of logic and imagination, where molecules dance, light bends, and electrons whisper the story of the universe. So the next time you see something ordinary, take a second glance. Behind every object lies a story, and behind every story lies science. If you enjoyed this exploration, make sure to like, comment, and share this video with others who love learning about the hidden wonders of everyday life. And don't forget to subscribe for more science-based explorations that'll change the way you see the world. Until next time, keep your curiosity alive and your mind open to discovery.